So welcome back. And let me open that. So well, there's so many people joining in today. For some weird reason. Okay. So tomorrow is a main thing, right? So next Monday, because I told you that I would have a conference in Beijing, so I would not be able to teach this class. So we will decide how to make up later. If we have time, if you have time, then we will do the makeup. If you don't, then we'll figure out how to do the makeup. I think we are able to cover everything we need to cover before the final exam. But I think like the last year, usually I would cover optional Python programming in the makeup class, which is not required for your exam. If you want, you can attend. That would be something we'll do it maybe in the B.B.A lab. That will be done in that manner. So don't worry about that the makeup time, because I know it's very difficult to schedule makeup for everyone since we have luxury of not so binding constraints. So probably that would be the thing. So second thing is I'm sorry that last class I think I have a technical issue where the video is not record. So I try to go a little bit slower. Again, go to review a little bit about what we have done last time so that you can take a note. And I also remember I said tomorrow is a Halloween, so I got some candy for you in case you want to take something during the break. Just some candy in case you want, and can just come out and get something, okay, whenever you like. You feel, I know everyone's very sleepy during the midterm, so come and take one. So there's a candy thing. Now let's get started. We need to review a little bit what we have done. So just to recall why we do hypothesis testing, right? The idea is to see whether the data is going to support what we think about the population, right? We want to see whether, say, the population mean is within some number there, right? Because we focus on simple hypothesis, right? We say, for example, in business application, we want to say, right, whether people are willing to pay for your product on average is like $1,000, right? Or we want to see whether you do a market survey, want to see how much they're making, you want to get in, right? Or how many people like your product, right? It's proportion data, right? So it's trying to see whether the data support what we think, right? And that is a reverse case for estimation, right? Estimation is I'm looking at data, right? And the data try to give us an educated guess what's going on in population. So we reverse it with some idea or some rough idea on the population parameter and want to go back to the data to see where data support it. Okay, so that is a kind of a reverse process. Okay, I hope that would be clear what we're doing. And the first part, we look at the one sample case, and then we go to two sample case, right? And very quickly, then we go again the slide, because I said I missed the video record, so probably I just quickly go over everything last time. So remember what hypothesis testing is, as I said, is just look at data and to see whether the claim or the idea we have in the hypothesis on the population is right or wrong, okay? And we have two terminology called null and alternative. And in our class, the null is always simple, means equal to some value, right? We hypothesize the mean is equal to some value, or the proportion of the population is equal to some value, right? In the application of what we see, say, in the election now, this day, right? We want to say how many percentage of people are supporting Trump or not, right? That would be one of the idea, right? Or that would be the thing we want to see, right? So the alternative in our class, we focus on the composite hypothesis, right? And simple and composite refer to the case where simple is equal to particular value and composite is more than one value, right? And either you have two different way, right? Either is sided, right? Not equal to or one-sided. It's more than or less than. And to decide which one is which, right, depends on application, right? Then you have to know when to apply to what, right? As I said, in the class, we focus on simple null and composite alternative, right? And just to remind you that in application, how in business application, when do we decide which one of the three type of the alternative being used? It depends on whether you want to take action, right? When things get bad, right? So for example, when you want to say, right, this candy, right? Then if you are health conscious, you don't want sugar content to be too high, right? You will have the alternate hypothesis when the sugar content is greater than certain level, right? And this is chocolate, so you want to make sure it's chocolate, right? So the chocolate, if less than certain level, then you would complain, right? That would be the issue, right? Mainly. And what happened? And when we use two-sided, right? It's very often when you care when the violation of the left and right will be a serious consequence, right? It's audit, right? Audit, you have to say that the number that given your client, you attest in the financial statement to be correct, right? Cannot be too high or too low, right? Anything that deviate will be violated, will not be happy. So you would use this not equal to. That would be the thing, right? So that would be the idea when to use what. I guess in assignment, right? In the exam, then probably you will be clear. I give you, right? But in your project, you have to decide which one to take, right? So, I mean, it's good you should know what to do, right? But often when your boss tell you what to do, but that'll be another case. But you should able to tell what should be the scenario. And we learned that when we make decision based on statistics, there are bound to be error, right? The reason is because we do not collect all data is available there. It's possible to collect, right? Because we only observe some part of the population, right? And there are two types of error. One type 1 error means that if true, it is true, but we wrongly reject it because we collect data as a randomness there, right? This is something we can control. This is called the significance level, right? Usually we set the rule of thumb is like 5%, right? Sometimes it's 1% or 10%, depends on application. But 5% rule is, I think, is the most commonly used rule in application. So, but otherwise, if you maybe look at big data, they may look at smaller one. But I mean, in application that you use in usual cases, it's 5%. Okay. But of course, you may say I want it to be as low as possible, but that's not feasible because if you lower this error, right, you increase the error of the type 2, right? Remember, right? The two type of error, right? One is, right, you reject the wrong null, but you may fail to reject it, right? If this is wrong, it's type 2 error. And that is not possible to reduce both, right? If you already have a optimal, the right test. So the only thing you can do it is to increase the sample size, right? But that would be, as you said, right? That part will be beyond the scope of our introductory class. So just to remind you what's a p-value. P-value will be you keep changing the significance level, right? Such that it just reject it, right? And this is feasible, right? Nowadays with computer. Right? In the old days, people rely on a fixed 5% rule, but now these days, and you can use p-value. More convenient because computer can do the calculation. So the p-value would be the way to go in these days, right? But still, the rule is still compared to 5%, right? But the p-value tell us how confident we are when you try to accept or reject. Okay. So as we said, for the one sample, we focus on sample mean because our introductory class cannot do sample variance. So, and to proceed in our introductory class, we need to make assumption, right, on the underlying population follow normal distribution, right? Otherwise, it's not easy to proceed, right? And we argue that it is a good assumption for application and they are background by central limit theorem, right? If you believe the underlying process follow that kind of thing, right? There's a summation of many random elements, then you can justify this, right? Of course, if not justified, then you will require much advanced technique that is beyond the scope of this class. Anyway, let's hope that this is true. It's hard to work if you don't know, but hope that this is true, okay? If this is true, then depends on we know sigma square, we can use Z test or T test, right? That would be the thing we do, right? And so how do we do this hypo testing, right? The idea is the following, just to remind ourselves again a graph, which I have drawn last class I now draw again because of the fact that I didn't record the last class, right? So if I have a observation, right, the population is follow a bell curve, right? I know the population variance like this, right? And the mu is this one, right? And there's a normality assumption, right? And if we have the random sample, right? That means that if I have n sample, right, it's still a bell curve, right? And with the mean mu, right? And we learned that will be the variance sigma square over n, right? Or the SD will be sigma over root n, right? That would be the assumption we learned, right? We learned the sample distribution two chapters before. And the question would be the following. Hypo testing is we have some idea on what mu is. We want to see the data support this or not, right? So the null hypothesis we would be saying, okay, now we know H null, mu is equal to A, right? So this is A, okay? And some number A, right? Maybe A is 16, this number we know, right? There's someone claimed that, okay? So the way to do the test depends on your alternative. Very, very important, right? So be careful, make sure that you know what alternative is. So to make our life easier, right? We just pick one of them, right? Mu bigger than A, okay? So we want to see if the data is in favor of the X1 instead of X0, right? It's more likely to be X1 or the X0. So you would say, okay, if I collect my data, okay, in my data, the sample mean tail was less than A, then we can go home, right? Because it's not going to be X1 anyway, right? If exactly A is not going to be matter, right? So, but we start to worry about X0 when mu is larger than A, right? But how large is large, right? Is 1 is enough, 3 enough, 4 enough? Unclear, right? So we have to quantify that by probability, like what we do in confidence interval, right? So it will be the case that we decide, right, if this area is small enough, then it's far above the A that we think is, right? And how to decide this area, how small it is, right? It's actually, we call alpha, right? But that's turned out to be actually the significance level, right? Because if this is supposed to be true, right? Assume this is true, right? You will say this is your claim. If this is true, the mean will be this particular value, right? This is the cutoff, right? We call this will be the critical value, right? Critical value, CV, right? Critical value is this guy, right? If your sample is beyond this value, then you would reject, right? And this could, if you remember the thing we do in the class, right? And this is exactly the margin of error, right? This confidence level, right? This guy is Z alpha sigma over root n, right? This guy, right? So this is the range that you would, the extension to that will be the upper limit that you will, beyond which you will reject, right? So this is large enough. And this turned out to be type 1 error that exactly you can control. That's why we can control type error, right? By changing the size of alpha, right? The smaller the alpha, the further away this high critical value, right? And just to remind you how to calculate this particular guy, right? This guy is from Excel, will be the norm S inward, right? And 1 minus alpha, right? The reason is you go to area to the bottom, right? Area to the value is inward, right? And you only invert from the left area, right? So you just 1 minus alpha is the left area to go back, right? So suppose alpha is 5%, then you just norm dot S dot inward 0.95, right? We did that last time, right? And this is the one way to check, right? And but of course, usually what we do is to calculate what we call the Z-score, right? The Z-score will be, the idea is just convert this guy, right, to Z, right, which is have 0 here, right? And where this area alpha, right, is exactly Z alpha, right? And they're the same thing, right? When this is, when your number is here, then you'll be here, right? So that will be, because everything, the bell curve can always, you can convert it to the standard, the standard normal bell curve, right? So that is how we do it, right? So that's why we call it, the test statistic Z, right, will be your data, right, X bar minus A over this guy, right? And this you can check whether it's bigger than Z alpha or not, right? If bigger than Z alpha, you reject, right? So this, the sample mean minus your A, your hypothesis, over sigma root n is the way they call test statistic. This is a number that is a focus, right? This is the formula that we look at, right? Is that okay? So this is the review of what we have done in the last class. Okay. And just let me quickly go back to the example. You see it again, right? Because as we said, right, in our class, the green thing is the most important stuff, right? You need to know how to operate that, right? And then the operationalize this is very simple, right? The main part is to understand what's going on, because everyone can understand this, right? You learn in high school, you learn this already if you do the M1, right? But let's understand what's going on, right? So let's see the example again, okay? So we give you this, the underlying distribution is normal with, this is 4, right? So again, what's going on is the underlying data, right, have variance of 4, sensitivity SD of 4, right? And what we want is look at this X bar, right? And we have sample size 64, so we have 64, right? N is 64, right? So, and what we have is this, right? The set SD is this guy, right? Which is the denominator here, right? 4 over 64. 4 over square root of 4, sorry, 64, right? And we know the sample mean is 7, right? And the hypothesis we have is 6. So 6 is what we think is here, right? 6 is what we think is this guy, okay? And what we have seen, right, is we want to reject if it's much bigger than 6, okay? And the data we have is X bar is 7, right? So if I told you X bar is 5, you can go home, right? We're done, right? Because the data is not going to violate it. It's done, right? The data is not going to be unhappy with the number. But the problem now is like 7 is bigger than 6, right? So you worry somewhat is like here, okay? It's here. So the question is, okay, should I say X1 or X0, right? Is it 6 and 7? Is it the difference of 1 is large enough or not? I don't know, right? So, but we learn probability. We can see how likely it might have, right? Is beyond 7 or more, right? How likely is this area, right? Is this area too large or too small, right? If this area is very small, then it's very far away, right? So you can calculate that, right? You can know how to do it because you learned it from last class, right? But what we do is we can do the Z-score thing, right? Just 7 minus 6 and divided by the SD, right? Look at how many SD from 6, right? Turn out to be 2 SD, right? That's what the Z equal to 2 means, right? 2 SD 2 SD away by construction is more than the threshold 1.64, right? Which is far away, then we reject, right? And just to remind you how to calculate this guy, right? This is simply just we have seen the last slide, right? Norm dot S dot inward, right? And because right-hand side is 5%, the left-hand side is 0.95. Okay. So look at this number, 1.64, then with 2, right? If you are 1.6 away from SD, then it's already done. It's all over. But it still is way far away, right? So you reject, right? Is that okay? Or you can calculate area on orange, right? That turned out to be 2%. So you still is very unlikely, right? If this is true, only 2% of time that you will see this or beyond. So it's very unlikely, so far away. So we would reject. So that's the idea. Is that okay? So we can do the same for the left-hand side, which I'm not going to repeat. But what I want to say a little bit is the two-side test. Okay, is this okay? Any question before I proceed? Okay, the idea, just repeat, is very important, is we would like to in favor of H1, right? If our sample mean is more than 6, right? If less than 6, we don't care. But how much more than 6 have to be quantified, right? We have to give some idea how to do, right? There's operational algorithm. It's look at the area beyond 7, right? And how small is this area? And this area you can calculate is turn out to be 2%. So it's too small that we reject. Or we look at the threshold, which is 1.64, right? Then you also reject there. Okay. So now let me get to the idea of the two-sided test, two-tail, right? The left tail and the right tail, the same idea. I'm not going to repeat. Just left and right twist your head is able to do that. Just the mirror image. And then we covered last time already. So the little bit problem of this is the two-sided. Okay. The main complication lies on the fact that the p-value, how to calculate, it be 2 times of that. Why is the case? And let's see the example. I can explain a little bit better. So actually the same question here, same data, but only different is the hypothesis is different, right? The same, exactly the same thing, right? Sorry, it's exactly the same as the previous one. So we have, again, right, from the question, X bar of 64, all right? And the hypothesis is 6, right? So we have 6 here, right? Mu is 6. That's what we claim. We want to see that it's okay or not. Of course, if your data is exactly 6, then we can go home. But the problem is the data we have is 5, which is somewhere here. Okay, 5 is somewhere here, right? Less than 6. So is it 5 sufficiently different from 6? The question is, right? And remember, before we have to decide what are the regions of rejection before we do it. Also, we don't know which side going to be. So we don't know going to be 5 or 7, right? We have to treat them symmetrically, right? So how is far away? You have to decide the range in both sides, right? So if you decide that the area will be small is alpha, that means that your fraction must be put alpha over 2 on one side, alpha over to the other, right? Because you don't know where to do before you bet, right? Because the data you draw can be on the left-hand side or right-hand side, right? So you put 5% on both sides, right? If it is too big or too small, you would reject, right? You say 6, right? You want to see what the difference of 6. So you would put the area on both sides, right? So you can put 5% on both sides, 2.5, right? That's far away, right? And remember how far away if you do this, right? This is just Z alpha over 2, right? Sigma over root n, right? This is, if you do this, is normal, right? So that will give you the critical value, right? You can compare your mean 5. Is it 5 is exactly here, right? Or 5 can be somewhere here, right? So you have to see, right? If here, then if this is the case, then you would go to, say, the data is rather aligned with H0. If it's in this region, then we will say is H1, right? If here also the same, right? If this, okay? Either the red area will say it's going to support H1. If it is not in the red area, then will be X0, right? Again, the easiest case is calculate the statistic, the same idea, right? Because you convert everything to the Z, right? To do the same application, right? And we're asking this, right, turn out to be 2 SD from the mean, right? You propose mean, right? So it's below the range is 1.96, right? Then you are going to reject it, okay? But the p-value have to be very careful, okay? The p-value be very careful. So now we know actually this is our guy is here, right? This is our guy, right? It's actually in the red region. So the question is, kind of the p-value have to be careful because the p-value, remember how to define p-value, is the significance level just made to reject, right? But you separate both sides. So you have to calculate area on the left-hand side, right? Which is this area, but give you over 2, so you multiply by 2. So that's why you have 2 times. You get that because we separate the area by 2, right? The significance level. So that's why you multiply by 2. So this is the only part that make things a little bit more complicated. But this is the only tricky part. But again, usually when you do Python or Excel, automatically give you this number. So you don't have to worry. Usually it's a two-sided test. In general, unless some special reason, two-sided test is something we employ in business application. Unless you pretty much know what's going on, right? As I told you, right? You auditor, you always do two-sided, right? But if you are doing something like, remember the chocolate and sugar, then you know which side you're going to. Then you have to be much more careful. The p-value are multiplied by 2 because you have to divide it by 2, right? Because the data actually give you is the two-sided one, okay? And the next thing we talked about last class at the end is what happens if you don't know sigma square, which is usually the case, right? Unless you have good estimate on sigma square, which usually we don't. I will also mention some way to estimate that. That is the most commonly done will be the replace the sigma, right, by S, right? This is the best thing we can know, right? Because we have learned that S square is the best possible estimator for sigma square, right? So we replace that, and then we know from the 2 chapter before, that will be the T, right? Okay, that is we check the T table, right? So everything goes on the same, the T, right? And just this example to remind you what we are doing, right? Remember, just to remind you that this is the most common case, right? This is the thing we do. And probably you would ask, right? And if you have a T, then why have to learn the Z test? The idea is when N is big enough, right? You know T and Z are very similar. So basically, that is almost essentially the same. When you have a large number of data, then not much different though, right? And remember, right? Why? Because when you have large data enough, right? The sample variance actually very close to the population variance anyway. So everything will fit very well when have data is large. But anyway, let's look at this again. So the first one is important because if you don't do that, then we cannot have T, right? And what we have is a random sample with sample size. This is go on, and what we want is this guy. We're going to test this, going to happen, right? Just to remind you, if this is true with a bell curve, right? This come, right? 16, right? We have the following feature. This is 4 here, right? And I don't know this guy, right? Sigma over root n. This is, we still have no idea what's going on. So I don't know how fat is this guy. Can be very thin, can be very fat, right? I don't know how it looks like, but it's a bell curve, okay? But I don't know how big it is. So the problem is, okay, I was told that the is 5, right? So, which is, now we know is here, right? The question is 5 large enough to tell us to support H1 rather than H0, right? Because if the data is less than 4, then we can go home, right? There's no need to do anything, right? The data is going to support H0. Now it's more than 4. Is it large enough? Okay. And the problem is we don't know how fat is this distribution. So we can't really do anything, right? Okay, we can't say, okay, how can we calculate this guy? How can we do it? I mean, we can't really go here. There's no hope of doing that, right? But the good part is we do know that, right? One thing is with the help of this sample SD, we know that the T, okay, which coming from X bar minus 4 here, right? Suppose this is true, right? Over S over root N, okay? Maybe I replace the S and N, right? Maybe I'll just copy the formula because T is here, right? So minus the A, right? S over root N, okay? Which is calculated in here. This guy have been proven follow a T distribution n minus 1 degree of freedom. Okay, so we know it's a kind of bell curve. If you subtract 4 and over the 2 over root 16, this gives you a bell-shaped style curve, but not the normal bell. It's a bell that is deformed a little bit, right? It's a hammered bell, right? Looks like this guy, right? Will be actually T15, right? N minus 1 will be a little bit fatter. So it's like something like that, right? Will be 0 is here, okay? And 0 refer to this 4, right? And where 5 will be actually number 2 here, right? It's 2 here, okay? And turn out to be, well, luckily, this area, very similar, it will be this area, right? So as long as we know this area, is it small enough, then we can make our decision, right? Because I cannot do in X bar, but I can do in a T, right? The T, we know how it looks like, okay? So turn out that 2 is sufficient far away because when you calculate this area is 3, okay? It's 3%, it's small enough, right? It's less than our threshold 5. So we say it's far away enough, right? So the only troublesome part is, right, as we can see here is, we cannot do it directly. We have to convert to this one. Is that okay? Okay. So this is, I think we cover up to here. So let me go to the left-hand side, see once again more, then we can know how to work on this, okay? And to remind you how to calculate this guy, right? How to calculate this area, right? In this one, how to calculate this number, right? How to calculate this area is how much, right? Just remember is T, this, right? Because from number to area, you pick 2 and 15, right? And area, remember this area is area on the left-hand side, so 1 minus, okay? So T this 2, 15, true. Okay, this is the thing, but this is left area, but you have 1 minus the right area. And how to calculate this guy, I think we mentioned last time as well. This guy, the critical area, which is the area that you would do rejection or not, right? It's the 5% on the right-hand side. So this will be T inward, right? 0.95, 15, right? Because the right-hand side is 5%, the left-hand side is 0.95, and degree of freedom is 15, right? Why degree of freedom, remember, is the shape of the bell in the T depends on how many samples you have, right? The more sample you have, the more closer to the normal, right? We learned that already. So that's why you have to check the particular table, which is 15. Okay, so that's the idea. Okay, let me do another one because I think that would be something that worth repeating because This is the same idea, but the left-hand side. So let's do this question again so that you have better idea what's going on. I know it's a little bit repetitive, but I want to make sure everyone on the same page because from the past teaching history, I know this is the part that I lost some of you. And majority of you actually failed to grab it. Although I know it's boring to repeat, but I hope that you would okay with me. So let me have this example again quickly. So with the same question, almost same question, okay? We have the normal distribution. We have the hypothesis in this one. So what we have is X bar, whatever you have, 9 or 16, because n is 16 here. So the random variable, right, is located at 4, okay? So the data tell us that it's 3, right? So it's actually here, okay? Now the question is, 3, is it going to favor x0 or x1, right? Which the data are going to support which one, right? And obviously, 3 is less than 4, so we have to check, right? If we get the data is like 5, right, or 100, then okay, go home, right? Because it's not going to be matter anyway, right? So 3 is less than 4, so how small it is, right? As we have said, we don't really know how to do, right? Because we have no sigma, right? Without knowing sigma, we don't actually know how is this area, right? Because this area, we have to see how far is look at this area, right? If this area is very small, then we say it's far away, right? But hard to see, right? I don't know how to do. But the good thing is if we write this in terms of t, right, which we know how to do it, we have t15, right? T15 will be this guy, right? That will be converted to 0 here, okay? And the 3 actually go to -2, okay? How to do that? This is X bar, right? And 4 is here, right? This is S. This is N, right? So this is saying that, okay, is 2 there, then we can know how to operate that. And that turn out, right, this is the blue area is here, right? This is the blue area, right? We want to see whether this blue area is small enough, that will be p-value, right? And to calculate that, right, because the area on the left, so we can directly do the calculation. If in Excel, right, that will be t, this, -2, tell them 15, right, the 15 table, true, and then we're done, right? This is the area, the p-value, and the Excel tells you is 3%, so is that then 5%, you reject because it's so small. It means that it's far away from 0, right? That means that 3 is far away from 4, then we're done, right? The data support x1, x0. Now, the other way to do is do the critical value, right? Look at 5% is where, right? The other way around is remind you that okay, let's look at this area, which is 5%, right? It's alpha, right? And if this critical value, right, depend on the 3 is bigger than or less than this value, then we do rejection or not, right? So we can do that, right? Look at the area is one way or the other, right? And the critical value going back to here, right, is to look at this number is 5%, this one, right? And this is inward, right? T inward 5%, the 15 table, right? So look at the 5% on the left-hand side, look at the 15 table, the T distribution will give us the number, which is 1.73, right? So, but that will give you the negative 1.73, right? That will be negative because Excel gives you negative 1.73. Then that is, well, you can see -2 is within this region, right? Past the threshold. So that's why you would reject it. Is that okay? So before the break, let me quickly go to the two-sided test, and then we call it break because that will be the last thing I want to mention quickly. So we'll do it quickly, same as this Z test, just to remind you how we do it. I know it's repeating myself many times, but it's so important that I don't want to miss it. Okay. So again, we have X bar. Because normal, X bar is also normal, right? No matter how time you do, right? We have N is 16. The hypothesis we have is mu is 4. So 4 is here. Okay. And this is this over 16, right? If this is the SD, it's decide how fat is it, but we don't know sigma square, unfortunately. Okay. And the data tell us is the sample mean is like 3, right? So it's here. So the question is, okay, is the data going to support X0, X1, right? And because before we do the sample, right, we don't know where it is, right? So we have to put the alpha on both sides. So how far is away from 4? We will have to assign, remember, is alpha over 2 here, alpha over 2 here, right? So the question is whether 3 is actually here or 3 is here, right? So it's whether, right? If in the case in the blue region, then reject. Otherwise, we don't, right? So this is something we do, right? If you know the sigma, then we're almost done, right? Because we know how the shape looks like, right? We're done already. But now we don't know, so we have to rely on this S, right? So which is again T15 here, right? Maybe I use the other color instead of red. So let me quickly finish this. Okay, this is T15 here, right? We have a bell curve, not exactly bell, but they deform the bell. This is 0 here. And what's 3? 3 turn out to be -2. All right, the same number there, right? The only change I have is change to X, mu not equal to, right? So same thing, right? And now you want to calculate this number here, right? Do note that the p-value have to multiply by 2, right? Because before you do it, you don't know where it is, right? The value calculated by 2. So what we do is 2 times what we have in the previous question just seen now, which now is 6%, right? Before one side is 3, so you don't reject, but now it changed to not equal to. Now you reject, right? Because now the p-value is higher than 5%, so we actually keep X0. So actually you can see by cheating, by, you can say, change X1, the result can change. So it's very essential to make sure that before you do the data collection, before you do hypothesis testing, you have to make your choice. You cannot cheat by at the end change it. Okay, that's cheating, right? You cannot adapt to it, right? You have to decide what is the two-sided or one-sided, right? Multiply by 2, turn out to be 6%, right? Actually turn out to be, this is the case, right? We have the here, right? Which is the first time the data actually support X0, okay? In the example we have seen. And we can also do the same, look at this value, right? And just to remind how to do this is just T inward, right? Because 2 sides, so upon 0.025, okay? And then 15. This gives you the left-hand side, right? If you need the right-hand side, it's just the same, but 0.975, but they are just negative value of the other, okay? So that will give you the idea whether you reject or not, right? So if you look at the alpha 5%, right, then it will give you this value, right? 2 point something. So basically what we have is this value here, right? 2.13 and negative 2.13, right? And this area add up to 5%, right? So it's not in the rejection region. So it's not far away enough to reject, right? So the question is, -2 is not far away enough, okay, to do it. Okay. And that explains a little bit interesting point is, right, in general, in management literature, right, they will say, if 2 SD away, then you will say, it's not the case, right? It's not going, it's going to reject, right? It's going to be far away, right? But you can see actually 2SD idea need not hold, right, in general, right? But of course, when n is big enough, then you find but n is small, the 2SD is not sufficient. So actually you have the more than 2 a little bit. So have to be a little bit more careful. So the management book, then the common wisdom 2SD sufficient. It's only true, right? We have seen, right? For the set standard normal, right? Actually, it's 1.96 is fine. That's a 2 comes from. But when the sample size is small, the 2SD idea doesn't really fit very well. We have to be a little bit more careful here. Okay? But that would be the idea. So I take 3 more minutes from what I supposed to do. So if no question, let's have a break of 15 minutes. In the meantime, that I recommend you to leave your comment or in the QR code. And let's have a break of 15 minutes, and then you can take candy while we have a break. Let's resume at 11:35. Okay. So I will go around to see if you have any question. Just remember to take some Halloween candy if you want to. Let's see what do we have here. So example page 43. So the T, well, this value, right? What we have is this guy, right? Remember T, this is T15, right? So this 0 here, okay? What we got is -2, okay? So remember, this is two-side test, right? So we have to put 5% on both sides, right? And the number we have 5% on both sides is 2.5, right? And 2.5 tell you is 2.314, right? So that means that we have 2.314 here and -2.314 here, right? 2.314, right? And this area is 2.5%, right? 0.025 if you want, right? And this is 0.025, right? And because of -2 is not in the blue region, so don't reject, right? Right? 2.314 is far away. We consider, right? Either negative or positive, right? Because we don't know which side. So the rejection region is on both sides, right? So that's why we don't reject, right? So that is a little bit different from the case where you know which side and you put all the area lump on one side. So you can more easy to reject. But we don't know which side, right? So that's why it's slightly more challenging to reject. Okay. I hope make it clear. But don't worry, we will do all this all the time. Hopefully makes sense. You understand more. Dot FEI and cross FET. Yeah. Yes, it's getting cold. So you see I have a long sleeve here. I've been getting cold. So please be careful. Tired candy help you stay awake. That's why I do. That's why I keep a lot of candy in my office. And when I tired, I just have that or coffee. So make yourself comfortable. That is fun. If you understand what's going on, it's fun. If you're not, then it can be a torture. But stat basically what is the we're doing is handling data, right? Do remember that you would handle a lot of data when you go to the working. If you don't know how to handle data, then more or less you will be outdated very soon, right? Because these days with AI, machine learning, all this kind of analytics, if you just use your head and decide whether good or bad, the time is over, right? In old days, good old days is the manager can just think, okay, this is good or bad, and then done, right? But now these days, there's so many days, so much data there, you cannot use your managerial instinct, whether you as impression of good or bad, right? You have the data come with you, and then you have to decide to analyze and to make a decision, right? So we become more scientific these days. So if you don't know how to handle data, then more or less I can say your future will not be very bright, unfortunately. Well, you will know, I mean, why I make prediction, because I'm economist, so that's we predict the future, right? So that is something that we know, right? Why my assignment was not graded? You have to ask the TA. I mean, let me ask the TA, because our TA is a PhD student. I'm supposed he's super busy anyway. But remind you that you submit it, you get 80% of the grade anyway, right? As long as you make a serious attempt on it, right? So the difference is like 80%, 90%, or 100%. So shouldn't be a big difference. But I will try to ask the TA to check it out. So not Friday yet. Yeah, I mean we think windy and cloudy because increasingly you're getting cooler. So please keep yourself warm. The speed is okay. Most of you can follow. I'm glad it. Lastly speaking, so the question is when to use Z, when to T. Very simple. Whether you know sigma. If you know sigma, Z. Doesn't know sigma, T. Right? Because you know sigma, then you know the graph, then because this is actually written in here, the slide. This slide here. Whether you know no sigma square, Z. Don't know T, right? Because you know the sigma square, you know the shape already. We're done. But you don't know that you have to transform the T, we can do things, right? We have to rely on sample variance. Oh yeah. Just next week, when we come back on Wednesday, make sure you stay warm. Otherwise, things can be a little more complicated. Okay. Oh, we have many things. So let's see some of the slide. Oh. Oh, why? Okay. So let's see our Instagram remark. Oh yeah, this is Halloween thing. I'm scared by this one. When I take my kid there, my kid also scared by that. So if you're brave enough, try this in the IKEA. So it can be fun. But I'm too scared to try. Have fun, enjoy it. What do we have? That's a YouTube. What YouTube do we have? But you know the song already, so probably you can check out if you like it, because I don't know any pop song, so maybe very, very important. Um, 10 hand, what's that? Is it something exam or what? But I don't know. Oh, 天寒, I don't know what that means. Trick or trick. Yeah, take the trick. Don't trick on me. Pure pain. Yeah, I guess that's what happened when you at the hypo testing. Either you like it or hate it. That's always the case. But you can see this. I mean, some of you actually asked me what's the use of this chapter. I mean, this chapter is so applied, right? Because remember, what we're doing is look at data and see whether what we know about what we know about the world is true or not, right? So that is very important, right? Because this is what we call scientific method, right? We look at data to see something is the real world just actually aligned with what we think, right? But anyway, let's finish the last test for the one sample. Okay, we go to two sample. So we've remember proportion data when the right, which happen to be the political pole and all the thing, right? Proportion is under the approximation, which is NP times N minus P. 1 minus P is bigger than 5, which is only assume is true. This thing is normal, right? With normal, then stun, right? So the only part have to be interesting is this A appear in the denominator, right? Because if we assume the mean is A, we already know the variance. Why? Because proportional data, right? We know that this is the mean, the variance is A times 1 minus A, right? This is sigma square, right? Right? That is the idea there, right? So that's why sigma square over root n, that's over there, right? There's a bell curve there, right? Because for proportional data, right? We know that P of n, right, depend on how many you have, right, must be under the null, A is here, right? This is must be the bell curve, and the variance is just A1 minus A, right, over n, right? This is the variance, right? For proportional data or binary data, right? The binary data that the sample mean, right, follow a normal, right? So that would be our thing, right? Just to remind you what it is, right? Just a graph, right? Remember, right? Our data is only 0 or 1, right? Maybe I just put it this way, right? With probability, right? If like P of X here, not the F now, right? P of X. X is 0 or 1, right? And this is pi here, right? This 1 minus pi, right? The data is only 0 or 1, right? But you look at this X bar over N, right? Which is actually P, right? The average value, right? The sample mean, right? We'll follow the pi here, right? And the variance will just pi 1 minus pi over n, right? That would be the idea here, right? So that would be, if you have binary data, and this is, we know, okay? Although the left-hand side is discrete, right? But if you have average of this, turn out to be a bell curve with, if you know the mean, you know the variance. So this is a very interesting thing, right? Because usually the mean and variance are separate. But when you convert this CO1 data, we already know the variance once we know the mean, right? So that means that everything the same, right? But we don't need to rely on T, right? Because this is something convenient for the purpose. So I hope you understand what's going on, but if not, that's okay, because what we need to know is to just apply, right? So this is a sample, okay, of binary data. You can imagine whether, say, they like spicy food or not, right? Or whether they like mirror, I mean, the band mirror, right? People hate it or like it, right? Some people like it, some people hate it. A lot of people go to the concert, right? And the question would be like this. We ask a random sample with size 50, and we found that half of people like mirror, right? Or you like error or whatever, right? So this 50%, and we want to see whether our assumption of 40% is right or not, right? So under this, we know this what happened, right? The sample proportion, okay, will be a bell shape with 0.4 here, right? The variance will be 0.4 times 1 minus 0.4 divided by n, and n here is 50, right? So that would be the idea there, right? We know exactly what it looks like, right? Because that is binary data, yes or no. So the good thing, yes or no question is, we know the mean, we know the variance, right? So that is the convenient part, okay? And now we have 0.5, okay? So again, it's here. Now the question again is it going to support H null or H1, right? In other words, is this 0.5 far away enough from 0.4, okay? And our H1 in this case is two-sided, right? So that means that I would assign 5% on both sides, right? Because before we do it, we decided two-sided, right? So what we have is this, right? We need to check, right? The easiest thing is to check this area, right? times 2, is it more than 5% or less than 5%? Right? Because we don't know which side, so we have to multiply 2. Right? But this is easy, right? Look at how many SD is it, right? So you minus 0.4 over the square root of that variance, turn out to be 1.44, right? Or look at that area, right? You can look at this area by looking at the norm, right? Dot S dot this, right? And 1.44, right? 1.44. True. Okay. Remember, this gives you the area on the left. So take 1 minus, give you the right, and you have to times 2. So that is the most complicated version you do. This gives you 14%. That's why you would not reject. Is that okay? Do you know how to calculate that is? You have to norm this 1.44, right? And do it, right? Why 1.44? Because you don't look at this one, right? We convert it to the Z here. This is 0, right? And use other color, right? Here, 0.5 is 1.44 here, right? So you want to find this area times 2, right? If this area times 2 is so small, that means it's far away from 0.4, right? Do you see that? Hopefully you understand what's going on there. I know I'm repeating myself many times, but I hope everything become clear. All right. So in this case, it's not, right? It's just too small enough, so you can't really reject this one. Okay. Is that clear? So you can see from this example, it's like if a 50 data actually 0.5, you still can't reject, right? So actually n have to be pretty large to reject this thing, right? So maybe you need 100 or 200 to try to say something reasonably well. Okay? Is that okay? Is that okay for this one? Right? So if you change this, if you don't like this one, right? If you change to more than, right? Then you don't multiply by 2, right? But then it becomes 0.07, you still can't reject, right? Of course, if you change to less, then you don't need to do anything anyway, right? Is that clear? Is that okay? Okay. Make sure they understand, because you don't want this step become a monster, right? For tomorrow, right? I don't know how you want to dress up for tomorrow, but I hope no one dress related statistics. Is that okay? So just to review what we have done, right? So we collect data, and that will be used to see whether our idea on the population mean is right or wrong, right? If you know the population variance, use the Z. If not, use the T. If the data is binary, that's even easier. The Z test will do everything, right? You don't need to go to T because we know it's normal. And we assume the mean, the variance already come up already. So it's very convenient. It's the binary data, right? So that's why it's a special case for binary data, right? Now, for the remaining time, we go to the other chapter. Okay. You can see it's very similar to what we do. We do the t-test, the remaining one. The only difference is the proportion and the dependent. So that's actually remaining 5 different tests. Okay. So we learn 2, z-test and t-test. Okay. And then we will learn the first 3 is a t-test, and the z-test and the f-test. So there will be 5 different tests. Okay. So we learn z-test and t-test for the normal data, and z-test for proportion data or binary data. So we have 3. Now we have 5 more. So at the end, we have 8 in total in your pocket. Okay, don't worry, this thing Excel can do it quickly, but we will just have to learn the theory behind, and Excel will tell you all the calculations. So what do we mean by two sample? Okay, two sample is the idea that you often compare two groups of data, right? Because usually we are not usually interested in looking at why we have the particular idea, what number of this, why this, we have the idea why population mean is one number, right? For example, the chocolate, right? By law, you say in the package, you say maybe 90% chocolate, then you can test, right? Or how many sugar you have, this is something to test, right? The data. But very often, we do not test this kind of thing. Rather, we want to know whether two groups of data are the same or not. For example, very commonly, you want to see whether man and a woman are earning the same wages, right? If not, we have discrimination, right? Or in business, you want to see whether different cities would have the same characteristic, how much they spend, right? Then you can decide you will set the same price for different city or different or same, right? That depend on how the consumption ability, right? How much they want to pay, then you may set different prices, right? Or you have two managers. You want to see if two managers behave the same or not, right? The earning ability, right? Because every month the number fluctuates, right? You want to see if you have sufficient evidence to say the two managers are performing at different level or the same level, right? These are all applications when we want to compare, right? And you also want to compare proportion, right? Like you want to see maybe right, how many people like this class, like this that class, right? Maybe women like this class more than men, right? Maybe they like data more, or otherwise, right? Or look at the best thing. Look at Swiss K, right? You know, we have old traditional college, right? We also have new colleges. We want to see whether maybe the old colleges people are different from the new one, right? Maybe they tend to have higher GPA or lower GPA. I don't know, right? And in my old days, I have 4 college, right? Only have New Asia, United, Seoul, and New Asia, Chongqing, right? Chongqing. And people joke at that time, people in Seoul are more laid back, right? Because they are in the other side of the mountain and not easy to get there, right? And people there tend to play around in the hall when they live there, right? More fun, right? And right, that's why we call, right? At that time, because 上台就入座啦. That's what we learned when I was a student there, right? So you want to lay back, you want to lie down, right? Then you go to Seoul College. But of course, I don't know how it is like the case, maybe different, but so it's a question, right? You want to see they are different or not, right? Two group people, right? So that is, you can test whether the GPA are different, you can compare the mean, or you can say whether they like to study or not, right? Comparing proportion, right? That is the two things. The last one is also important. You want to compare variance, right? Why you want to do that? Remember, variance what? Variance the investment is risk, right? You want to compare two set of investment, they're the same risk or different risk. Then you look at the F test, which we'll cover at the end, right? Or in the investment, you want to compare two investment opportunity. Are they the same mean or different mean, right? Look at the compare the return, right? So that would be the way that you would look at, right? And you can also compare proportion. If you divide the data into days in the good time, days with losses, right? Binary data, right? Each day, then you can also use a risk measure. So risk can be done in finance in this framework very easily. Okay. So we start with some notation. Okay. Why notation? Because it's getting increasingly complicated, so we need some notation. Okay. And here we only consider two different grouping. Okay, you want to compare different groups. Okay, either saw or non-saw. Right. So now you want to compare more. Right. You have 8 colleges. Right. I think now it's 8. Right. Then you want to compare different colleges, different or not. Right. More than 2 groups. So what to do is next topic we'll talk about ANOVA. That will be compare means across different group, the same or not. That will be the topic that we learn later. But for the moment, we only have 2 groups, right? Because in traditional, we have gender, we have male or female, right? But now in the US, we have more than 100 of gender, right? We have airplane, we have kangaroo, we have many different types of gender. So 2 group will not be done. We have to do the ANOVA to have 100 types of genders. You can put there. You can run. You have to do ANOVA. But if you want to 2 group, maybe male or non-male, that can be still be 2 group, right? So, but so the data is like this. We have 2 groups. We have mean, mu, and variance sigma square for each group. Okay. Observation is x11, x21. Okay. With x1n the same as this one. Okay. And you collect the data. This is called the sample mean, x1 bar, x2 bar. Okay. And if you have simple random sample, this is mu1, right? The sample mean of expectation mu1, this is sigma 1 over n1. So that is the idea. Okay. And the sample variance defined this way. It's the same idea. Okay. And that is unbiased. We'll give you this one. And this throughout we assume this is normal. Okay. And that's why the sample mean also normal. Okay. So probably you see too many description. It's easy. I'll give you a graphical explanation of all. So this is what we have. Imagine we have population 1, P of 1, right? With mean mu, sigma 1 square, okay? And you pick up one value here, right? It's random sample, say x1i, okay? We have mu1, right? Sigma 1 square, right? So that is the idea, right? When we randomly draw a number there, that should be following the same bell, right? The distribution is same as the original one, right? So if all the data you draw on will same as original one, okay? If you draw a sample here, you draw many of them, right? You draw any of them, right? You just x1, right? Will be same as x11 plus x12, up to x1n1 over n1, right? You draw n1 of them. So this is still a x bar n1, x bar 1. It's still a mu1 and a bell curve, right? But now your variance is this guy over n1 because that's how many you got, right? So that's what we have, right? We are drawing the data from there, right? Underlying data is normal. So that means that you draw each one is still a bell curve. Average of them is also a bell curve, but the variance slashed by n1, right? This is what we have. And similarly, this is a bunch of men, right? maybe be a bunch of women here, population 2, right? And the data is distributed with normal, mu2, right? Whenever you just try to draw a data, there is 2i, okay? And the variance is 2 square, right? And when we draw a number here, it will be drawn from this, right? That's what we call this random sample. And if you draw n2 of them, right? Average them out will be x bar 2, right? We'll have the sample mean mu2, right? The variance will be mu2 squared over n2. Okay? Is that clear? So the actual question what we have right now is the following. We want to see the H now will be the data supporting that the same mean. Or I make it simple. I focus on two-sided test. You can do the one side same. Or the not the same. Say men and the woman are different or not. Okay. The question. Or people from store are different from others. Okay. That's no big sort. Maybe pick Tongji College is different from others, right? Because they're only one in the lower campus, I guess, right? So that would be the question. So the idea is I got a number here, right, from the data. And I got a number there from the data, right? So the question would be, is it they're different enough or not? Okay. So that will be the question. That's the question. Okay. So how do we proceed? Okay. So we have to realize the following. Okay. We know that x bar 1 we have seen is a bell, right? With mean mu1. This is the variance, right? We have said. Okay, I just copy from the previous slide. Okay. This is the diagram we have. So the question would be, hey, we get the data, which is, I don't know, this number here, and the number is this here, right? So it's the data actually we got, okay? So how do we proceed? Is it the same or not, right? If the number actually the same enough, then we are okay, right? But we don't really know, okay? So the question would be the following. First, we need to come up with the idea, what would expect this would happen. Maybe it's the color. So we look at this thing. I know it's this color. What is this guy? What should be this guy? And if you call 2 bell, subtract, still a bell, right? So what we have is this is mu1 minus mu2. It's still a bell. Okay. And this one is sigma 1 square over n1 plus sigma 2 square over n2. Okay. So that would be the idea, right? So if you want to say, see if the number is the same, right? You calculate your data, look at the boys mean and girls mean, take a difference, right? If under the null, this is 0, right? The null hypothesis, right? The null is like this. H null we are trying to see if they're same or not, right? If this is equal, means that this is 0 here, right? So if we want to say this is not equal, that means that we are trying to say if this is far away from both sides, then we reject, right? In the case that we know sigma square, that is very simple. This is our solution, right? Same as we see, right? Depend on data. If the data is inside the orange region, we reject x1, right? If not, we reject x0, right? So if not, then we accept x0, right? If inside, then we reject x0 to the x1, right? In favor. So that is the same idea, right? There's nothing new there, okay? The only complication is, which we focus on, is we don't know this guy. We have no idea of sigma 1, sigma 2, okay? So that's why we have to come up with 2 ways to figure that out, okay? So if we have no idea x1, sigma 1, sigma 2, okay? Then we have to replace by s, right? And this would be following the t distribution, right? So we replace sigma by s1, s2, then we get a t, okay? And that will be the second test we have. But in a very special case, if we have another assumption whether we know sigma 1 is exactly the sigma 2, okay? Which means that the boy and girl have the same shape, just different mean, easier case. Then our life is easier because we can estimate these sigma using the whole data set. Okay, then the formula is different. Okay, to be sure, let's see the slide, which I'll go into detail later. So this is all I have already, right? This is just this graph here, right? And the only complication you will see soon is if we make the assumption that the boy and girl have the same spread, same variance, we can come up with a new estimate of the variance SP as a way to estimate sigma the same. This is a better estimate. And once we did that, the formula is like this one. This is the key. Okay. In this case, we have better estimate on this one. And I will only check this table. Okay. Which I'll go into detail more next class. Okay. But if we can't make the assumption, then we will have to rely on the sample variance for each. And this table to check will be super complicated. This V is come from the most monster expression, which will fit your Halloween. This will be the formula to calculate the table you're going to check. Okay, this is Halloween table. Okay, so that is the thing. So it's not complicated, right? So take the mean difference, do the bell, check the t table, right? There's a monster thing. This is only monster thing in our class. Don't worry. It's the maximum. Remember, you don't need to remember it, right? Because this is already in the slide. Okay. So I should end here with this monster slide, so that you can have fun with Halloween. You can print that on your T-shirt, right? If you want to scare away your friends. Okay. I will see you next Wednesday. Remember, Monday no class, so I will send. I put an announcement again. This one you have that. You have the set table. Yeah, you can check 1.44. You can check. It's on a table, then you can do it, right? So the normal can have table.